All right, we're going to take a look at 3.6, number 10, because a thoughtful student asked, how did I know I was supposed to use work in my solution for this? The short answer is I didn't know that I was supposed to use work, but I chose to. So we're going to look at two different ways of solving this and compare, let's say, a third way, which is actually equivalent to the second way. So there are two definitely different ways you can go about solving this. One way would be to look at this entire situation, recognize that it is some kind of a modified Atwood's machine, and consider all the forces acting on these things. On the large mass, we've got its weight acting downward, and we've got a spring force acting downward. So we've got two forces there. And on this small mass, we've got one force acting downward, or the opposite direction to the left, and that is the parallel component of its weight. And so when we consider the sum of the forces, we've got three forces, and the acceleration is the sum of the forces divided by the total mass. So that would be the total mass in this case would be both things moving together. So the grand total of the forces would be big mg plus the spring force plus mg sine theta, actually minus mg sine theta, all over big M plus little m. Now, we quickly run into the issue that unlike previous problems where all of the forces were constant forces, in this case, well, mg is a constant force, mg sine theta is a constant force, but the spring force is not a constant force. So unlike other problems where this method actually was an option, in this case, it becomes less of an option. We could probably find a way to do it, but it's cumbersome because if you're trying to find the acceleration with varying forces, it's not convenient. So we're not going to go that route. So then the question is, like, how did I know I was supposed to use work? Well, there's two ways. If you're going to just go the pure energy route, there's two ways to interpret this. One way is to recognize or just kind of lean on the idea that the network is equal to the change in kinetic energy, which is to say that the work done by each force, the work done by the first force and the work done by the second force and the work done by the third force, there are three forces, all add up to find the change or reveal the change in kinetic energy. So there's one direction to take, which we will do. So the work done by the big mg, well, that's pretty easy because mg is a force. So we've got a force and we need a displacement. And since block M is pulled 20 centimeters down the incline, so basically what we're going to do is to sort of load this thing up, we are pulling mass 1 backwards, pulling it down the incline, and then letting it go. So once things are released from rest, the system, well, is going to be sort of going in this direction. So one of the forces driving the system is mg, and that's pulling things down. So we've got big mg times the distance that it travels through. So what's the distance? It says the spring is unstretched, frictionless, angle of incline, blah, blah, blah. Find the speed of block M, which will also be the speed of block big M because they're attached, when the block M is a distance above the floor at which the point the spring is unstretched. So recall earlier that we stretched the spring 20 centimeters down. So the spring stretch is 20 centimeters, and that's also going to be the distance that everything travels for the points that we're interested in, and that's also going to be the height for the mass that this thing travels through. This height here is kind of irrelevant because the mass isn't going to go that far, or I suppose it could, but we're not going to pay attention that long. So this height is kind of irrelevant. It doesn't really matter where the floor is because we're not going to hit it. So the mg, the work done by gravity on the big mass, pulling it down, is going to be mg times, I guess I'm just going to call it d for convenience, and kind of leaning on this over here. The length that the spring got stretched is the distance that things will travel. So we've got the work done by gravity. Now, that's kind of easy because that is a force times a distance, right? Constant force times a distance. Now, the work done by the spring, again, we come into that issue of the spring force is not a constant force, but we know that the energy, the potential energy in a spring, well, once you've released it and you've used up all of that potential energy, that becomes energy that the system has. So essentially, the energy contained within a stretched spring is energy that will be introduced and work done on the system. So although we don't have a explicit force times displacement, we can say that the energy in the spring is going to be doing some work on the system. So 1/2 kx squared. So that's going to add energy to the system. And finally, we've got the mg sine theta, which is acting against this. Things are moving to the right or clockwise, and this mg sine theta is in the opposite direction. So that's going to present some negative work, that's again kind of easy because it's going to be FD, force times displacement. So that's going to be negative. So we got little mg times sine of theta times d. So we've got the work done by 3 independent forces, and all of those, when we consider together, will give us the change in kinetic energy, which would be kinetic energy final minus kinetic energy original. And since it was released from rest, kinetic energy original is 0. So we can plug all of our numbers in. We've got the big mass. We know g. We know the d. We know k. We know x, which is the same as d. We've got m. We've got g. We've got the theta. We've got d, which is the same as x, which is the same as d. And all that's left is 1/2 mass times velocity squared. And this is where both masses need to be considered, because the kinetic energy of the entire system is what we're considering when things get moving. All right, so I'm not going to plug it in because the rest is just plugging and chugging. However, what we'll consider is how this is similar to or different from looking at it a different way. So the way we're looking at it here is from the perspective of network equals change in kinetic energy. Well, what if we look at it from the perspective of conservation of energy, like the energy at the beginning equals the energy at the end? Well, we could say that the energy at the beginning is, this big mass is going to fall some distance d, and so the height through which it's going to fall is going to imply that it has some potential energy. So we've got the potential energy of big M at the beginning, and of course we have the potential energy of the spring. That's easy. That's set and ready to go. At the beginning, if we say when we draw this little m back to this point, right over here, for its sake, let's say that that height is 0 for its potential energy calculation. So the potential energy of the little mass, we'll just call that 0, and nothing's moving, so there's no kinetic energy. And all of that is going to turn into, well, at the end, if we say that the height of the big mass is 0 when it falls, then we can say that the potential energy of the little mass later at the end, we can call that 0. But in the process, the little mass has gained some height. So one important thing is to recognize that that calculation for height and that one might not be the same, since little m is going up at an angle, but it is going up. So let's think about what that energy is going to be. So it's going to be, we're going to call it for the moment UG little m at the end. And so the big one goes down, the little one goes up. So the big one's potential energy turned to, became 0. The little one's initially not having a potential energy became some, but then the spring energy became 0 because at the end, because it was released. And then finally, there's going to be some kinetic energy of the system. And so when we kind of get rid of all of the things that are 0, and we look at the left and right, they are kind of similar, which I suppose, let's say, all right, if this is positive, the little mass gained some potential energy. Well, on the right-hand side is positive. If we move that over to the left, that's would allow us to rewrite UG of big M plus the spring energy minus the energy gained by the little mass, G little m, equals the final kinetic energy. And so then the question is, well, these are starting to look really similar, right? We've got mgd, and that would be big M times G times the height, or the D, or whatever it falls. So that's equivalent. The spring energy is equivalent. And then the question is, are these equivalent? And, well, the short answer is they have to be, but the slightly longer answer is, how are they equivalent? And so we've got the increase of potential energy of that one. Well, it's going to draw a little triangle. If it's going to move a distance of what was it, 20 centimeters in that direction, then we need to know the height that it moves through. So we've got the angle here. So d sine theta would be that height. So this expression becomes little mass times g times d sine theta, which, if we rearrange it, mg sine theta times d is, in fact, exactly the same algebraic expression as it looked like if we had considered it from a work perspective. So looking at this from two different perspectives, either the work is the net work is the change in kinetic energy, or from a conservation of energy at the beginning equals energy at the end, they're in fact mathematically equivalent.